So for this section 4.2, we're going to be looking at graphing exponentials, at solving exponential equations by matching the base together, and looking at some present and future value stuff. So it's going to be exponential equations. And basically exponential equations, these are equations that all have the form f of x equals a to the x, where a is positive and a can't equal 1. So we're looking f of x equals a number raised to the x power. So we're going to look at, first of all, suppose we had f of x equals 3 to the x, and we want to figure out what's, let's say, f of 2. So this right here is pretty straightforward. A couple of you guys' homework problems are going to start out like this. So if you want to figure out what f of 2 is, you just replace the x with 2. You get 3 to the second power, which is 9. If you guys have a fractional base, so like f of x equals 1/4 to the x, and we want to say what is f of 2, this would be 1/4, oops, 1/4 squared. When you guys square a fraction, you get the top squared over the bottom squared. So this would be 1 squared is 1, 4 squared is 16, so you get 1/16. If we have a type where there's a negative power, so let's say f of x equals 4 to the x, and we want to find what's f of negative 2, this would be 4 to the negative second power. When you guys have something raised to the negative power, this becomes 1/4, and then the power that it was raised to, the negative 2, becomes a positive power down in the bottom of the fraction. So this would also give us 1/16 in this case. So using this idea, we're going to plot some points and use those points to generate graphs of exponential equations. So we're going to start out with our first one of these graphs, wanting to graph f of x equals 3 to the x. When you guys want to graph these, I think the easiest way to graph them is to go through and just look at it. Let x say equal -2, -1, 0, 1, and 2. And then you guys are going to graph, your y values will be 3 to the x power that you chose. So I'm just kind of randomly choosing these 5 points because they're easy to work with. And if I can get where the points of the graph are based on these 5 points, I can get a pretty good idea of what the graph should look like. So 3 to the -2, that's 1/3 squared. That's going to be a 9th. Whoops. Hang on, my pad thing started drawing. 3 to the -1 is a 1/3 to the first, which is a third. 3 to the 0, anything to the 0 power is 1. 3 to the first is 3. And 3 squared is 9. So on our graph, we have x values -2, -1, 0, 1, and 2. And the y values are going to start out at a 9th and go all the way up to 9. So we get 1, 2, 3, 4, 5, 6, 7, 8, 9. So when our graph is at -2, we're at a 9th. When our graph is at -1, we're at a third. Then we're at 1. Then we're at 3. Then we're up here at 9. And our exponential function will connect through these. This exponential function will have a horizontal asymptote at y equals 0. So there's just going to note there's a horizontal asymptote at y equals 0. Basically, this thing will run along the x-axis. It will never hit the x-axis. It won't cross over. So this kind of function here is going to just pinch down on the x-axis and run alongside it. It didn't ask us for this, but the domain of this would be all real numbers. And the range would be, we never get the x-axis. We never get below the x-axis. So The second you get a little bit above the x-axis, if you go really far over to the left, you'll find the function. So it's basically just all positive numbers would be the range of this function. So we're going to do one of these with the fractional base, and then we'll take a look at a special number called e, which is kind of like pi, and we'll see how to graph that, and then we'll look at some change of base stuff, or matching base stuff, I guess, and then we'll do some present and future value stuff. So let's see here. For this one, we want to graph f of x equals 1/4 to the x power this time. So again, since we want to graph this, we're going to build our table of values. We got -2, -1, 0, 1, and 2. So we get 1/4 to the -2, 1/4 to the -1, 1/4 to the 0, and 1/4 to the first, and 1/4 squared. So when we want 1/4 to the -2 power, this is going to be, when you guys raise a fraction to the -2 power, the fraction flips over. So we're going to get 4/1 to the +2 power, which is going to be 4 squared, which is 16. So 1/4 to the -1 power will be just 4. It would be 4/1 because the fraction flips. Anything to the 0 power is 1. 1/4 to the first power is itself 1/4. And 1/4 squared, you square the top, which is 1 squared is 1. Square the bottom, which is 16. So for this one, I'm not going to be able to graph -2 because it's up there at 16, and that's pretty tall, I guess. So we're going to just kind of keep in mind that at -2, we're way up here at 16 somewhere. At -1, our y value is 4. At 0, our y value is 1. At 1, our y value is 1/4. And at 2, our y value is 1/16. So our graph kind of drops down this time instead of getting bigger. And it has a horizontal asymptote along the x-axis still. But instead of staying small and then growing larger, it comes down from being large over to small. Real quick, let's look at Desmos with these. This graph here, just take a look. So we got 1/4 to the x power. See here, so we want to do 1/4 to the power of x. Whoops. And so we can see here that the graph drops and then it runs along the x-axis. And so I've kind of drawn it not very good here, but this basically we can kind of see this graph looks kind of like we've drawn it. It blows up as you move to the left, it gets bigger, and then as you move to the right, it pinches down on the axis. So next number we need to talk about and then build its graph is e. And we can see here e is about 2.71828, etc. It's a number like pi. It just is a big decimal string. We're going to use about 2.718 for e. So e in this is going to be about equal to 2.718, and it just keeps going like pi does. So let's say f of x is e to the x, and we want to graph that. So we'll say, all right, let's get our table, x's and y's. X will be -2, -1, 0, 1, and 2. And y will have e to the -2, e to the -1, e to the 0, e to the first, and e squared. E to the -2, this will be 1 over e squared. E to the -1 will be 1 over e. Anything to the 0 is 1. E to the first will be e itself, which is about equal to 2.718. And e squared, let's see, what is that? So whatever 2.718 squared is, e squared will be about 7.389, so 7.389. And then, so if we kind of go to graph this, when our x is -2, 1 over e squared will be 1 over 7.389, so it'll be kind of around a seventh. It'll be between a seventh and an eighth, so it's down here. Since e is 2.718, 1 over e is a 1 over 2.718, so that's bigger than it's going to be smaller than a half, but not quite a third, because 2.7 is close to 3, so 1 over 2.7 will be kind of close to 1 over 3. So this is going to be kind of around a third. E to the 0 is 1. E to the first power is 2.718, so 2.7-ish, a little bit. And then e squared will be at 7.389, and again, for 2, that's going to be up here kind of. So we can see what our curve looks like for e to the x. It grows kind of like this. If we want to graph it, Desmos, just take a look. Let's see what e to the x looks like. It'll be a exponential curve that looks like this. So if you guys want to graph an exponential function, this is basically how we're going to do it. You guys go through, build a table of values, use some easy to work with x's, generate the y's, and then plot the points. So the next thing this section is going to build on is all that transformation stuff from section 2.7 can apply to these exponential functions. So what you do is you have to figure out what is the base exponential function, and then you move the base exponential function around. So we're going to look at graphing a couple different ones of these based on 3 to the x's graph. So we want to graph what if f of x equaled 3 to the x minus 2. What if f of x equaled 3 to the negative x, and what if f of x equaled 3 to the x minus 1 plus 2. So we want to see what happens in these cases here. So our base function is going to be 3 to the x, and we drew 3 to the x's graph a bit ago up here at the top. So 3 to the x's graph was this first one we drew. So that's going to be our starting function for each of these. So it has a y-intercept at 1, and at x value 1, the y value is 3. So we have our curve kind of like this. This is going to be the starting graph for each of these. So this will be our base graph. When you guys subtract 2, 3 to the x like this, for these exponentials, if you're in the power, that's like being inside the function. Anything that's not in the power is outside the function. So this minus 2 is outside, so that'll move our graph down 2 units. Over here, this negative up top, that's like a negative being inside the function. That's going to be a reflection. It'll be a y-axis reflection. And then over here, a minus 1 up top, that will move you. You expect it to move you to the left, but since this is inside the function, it works backwards. This will move you to the right 1, and then this adding 2 is outside. That'll move you up 2. So these are kind of the transformations for each of these 3 cases. This is your starting graph. So for A's answer, all we have to do is take the starting graph and push it down 2 units. I'm going to use a dotted line to represent the horizontal asymptote that this thing used to approach. So it goes along the horizontal asymptote, and then it pulls up here, and it basically just keeps growing exponentially. And so we just have this graph, and we just push it down 2 units, and that'll be our answer to A. To B, you just flip this graph about the y-axis. So for B, we get 1, 3 is now on this side, and our graph drops down and runs along. You just do a y-axis reflection of this base graph here of 3 to the x. For part C, we move this graph left 1, then up 2. So I'm going to draw in the new new horizontal asymptote. And I'm just going to kind of follow this point here. When I push it to the left one and then it goes up 2, it'll go left 1, then up 1, 2. So this will be where the base graph where it clipped through the y-axis. That's where that point gets sent. So we will have our graph growing like this. That's basically it. So for the graphing of these things, all your 2.7 stuff applies. If you're up in the power, that's like being inside the function. So stuff that occurs up here is sort of inside, and stuff that's like down here or out in front, that will be outside of the function. So you guys can apply your 2.7 stuff to this pretty easily. Let's maybe do a base graph in Desmos and just look at a couple things on kind of how it changes. So let's say we had 4 to the power x, and we can see, all right, if let's say I add 3 up here in the power. If I add 3 in the power of 4 to the x, that should move my graph to the left 3. So I add, whoops, I can't. Awesome. Well, apparently I can't add in the power on this thing. Oh, that's great. Okay, so maybe if we do it with parentheses, that's what we need. Okay, there we go. So x plus 3, we can see that moved our graph to the left 3 units. If we're down here, if we subtract 3, that moves the graph down. If we added 3 outside, that moves the graph up. Negatives down here, we'll do x-axis reflection. If we have a negative up in the top of this, let's say to the power, say a negative x up there, that does a y-axis reflection. So all the transformation stuff that we dealt with earlier, it all applies here, where if you're inside the function, that's like being up in the power right here. This is inside the function, and things occurring out here or in front of the 4, that's being outside the function. But all that 2.7 transformation stuff carries through to these exponential formulas. Okay, let's see here. So the next group of problems want us to solve exponential problems by getting the base to be the same. So if we have, say, a to the x equals a to the y, if we have 2 exponential formulas and the base are the same, then the powers would have to be the same. And for like a basic case, like say we had 5 to the x equaled 5 squared, you say, well, how do I make 5 to the x the same thing as 5 squared? If these are going to be the same, then x would have to equal 2. We can kind of see that then we get 5 squared equals 5 squared. We can see that this makes sense from a statement like that. So what we're going to do is kind of get more complicated versions of this, where we use that idea of matching the bases and then setting the powers equal to each other. So suppose we had 25 to the x equals 5. What I'm going to do to solve this, I need to make this side a 5 to some power as well. So 25 is 5 squared, so I'd get 5 squared to the x equals 5. Power to a power multiplies, so this is 5 to the 2x equals 5. And then 5 is 5 to the first power, if we think about that for a minute. Now we got these both the same base, different powers. So to solve this, 2x would have to equal 1. You divide the 2 across, and you get x is 1/2. So you start out with the statement here, you make the bases match, and you get x equals 1/2. And you may say, well, what if, instead of 25, if that was a 24, we wouldn't have the bases even, they wouldn't be able to match the bases. And then this process breaks down in those cases. We'll see in section, I think it's 4.5, how to handle those types. But for this homework section, all the problems will be kind of set up so that so that you're able to solve them by matching bases. So let's look at a couple more of these types. Suppose we had 2/3 to the x power. So 2/3 to the power x equaled 27 over 4. So I need to get 27/4 down to 2/3. So we say, well, 2/3 to the x power. Let's see here. Sorry, I set this problem up not very good. This one's actually a 4.5 type. We can't solve it using this method. Let me say we had 2/3 to the x equals 9/4. This one will be okay. So sorry about that. So we get 2/3 to the x power. This would equal 9 is 3 squared and 4 is 2 squared. So this other type I just scribbled out, it wasn't going to be able to be solved by this method because I got the 27 should have been a 9, so I set that up wrong. So that type I scribbled out, that would be a type that we'd have to use the 4.5 method to solve because the bases didn't match, or there wouldn't be a way of getting this matching base stuff to work that we're going to do here. So the ones in your homework will be set up to work like this. So we say, well, we got 3 squared over 2 squared, which we could say is 3 halves squared. And I got a 2/3 here and a 3 halves there. So I need to flip the fraction 3 halves over. So to flip the 3 halves fraction over, I can raise it to the negative first power. So I get 2/3 to the negative first squared. This should still be x. So 2/3 to the x equals 2/3 to the negative first squared. So 2/3 to the x equals 2/3 to the negative 2. And at this point, we can solve it and say, well, it's same base, different powers now. So x would equal negative 2 for our solution there. Okay, next type. We want to do 2 to the x minus 3 equals 32. So we need to be able to write 32 in terms of 2. 32 is 2 to the 5th. So same base, but different powers. So now you can set the powers equal to each other, and you're able to solve them from, solve x from there. So we add the 3 across, 5 plus 3 is 8, and we get our solution. So these types, mainly, you just kind of got to look at it a bit and think about what's the common base that I can get these things down to, and then you're able to go from there. So suppose for this one we have e to the 5x minus 2 equals e to the 13 to the x power. So when you have power to a power, they multiply. So we can get this is e to the 5x minus 2 equals e to the 13x. So now they're both base e. So I can drop the base and just let the powers be set equal to each other. I'll subtract the 5x's across. So I get negative 2 is 13 minus 5 is 8x. We divide the 8. Negative 2/8 is the same as negative 1/4. So we get negative 1/4 equals x. Okay, so same base. Once you get same base, you ignore the base and just set the powers equal and kind of go from there. We're going to do 1 or 2 more of these types. Then we'll switch over to present value and future value stuff and finish out the section there. Okay, so let's see here. This one, we got 8 to the 4x minus 1 equals 16 to the 2x plus 3. 8 is 2 cubed and 16 is 2 to the 4th. So I'm going to take these both down to base 2, or exponential base 2. And we said power to a power multiplies. So this is 2 to the 3 times 4x minus 1. And this is going to be 2 to the 4 times 2x plus 3. So same base, different powers. We're able to ignore the base at this point and set the powers equal to each other. And then we just solve out the equation based on those two powers. So we distribute the 3 on this side, distribute the 4 on that side. And then we're going to subtract 8x. And we're going to add the 3 across. So let's see here. 12x's, take away 8x's. 12 minus 8x is 4x's. And that equals 12 plus 3 is 15. So divide the 4 across. And x is 15 fourths for that one. Okay, for the final stuff that's in this section, it's present value and future value stuff using interest rates. So there's two equations. They're based on how interest is compounded. So we're going to set up the first equation where interest is compounded n times per year. The equation will be A equals P times 1 plus the interest rate divided by the number of times you compound per year times MT. The other way is continuously, which will be A equals PE to the RT, where E is that 2.718 number that we were dealing with a little bit ago. So in these equations, P is the principal. It's the initial investment. It's also it's called present value also, because it would be the amount of money that you would put into an account. So we use PV for present value. It's the amount of money that you're putting into the account, say, today. A is the amount in the account at time T. So that's the amount your account grows to. Like if you invest $1,000 today into an account, you let the account go for 8 years, then A would be the amount in the account after 8 years. So this is our future value. This is the amount the present value grows to. R is the interest rate. Interest rate, you have to put it in as a decimal. So if you guys have 15% interest rate, use 0.15. If it's a 2% interest rate, it's 0.02. So you have to convert it over to an interest rate. And then T is time in years. In this equation here, N is the number of times you compound per year. If you guys have, say, annually, N equals 1. If it's semi-annually, N equals 2. Quarterly, N equals 4. The other common ones are kind of monthly, which would be N equals 12. And then daily, be N equals 365. So for those are some of the different compounding values. It's basically how many times, if it happens quarterly, it happens 4 times a year. If it happens monthly, it happens 12 times per year. It's 12 months in a year, etc. So depending on what words we see for these, this tells us kind of what the different values for N we use. So let's do a couple problems with these to finish out, and then that's basically everything in the section. So let's say that you invest $2,000 at 5% interest rate for 6 years. And we want to know what's the amount in our account. So let's say what's the future value if interest is compounded in part A, we'll say monthly, and part B, we'll say continuously. So the future value will be A equals, for the monthly, N is 12. We're using the first equation, so A equals P, the principal investment, which is $2,000, times 1 plus the interest rate is a decimal. 5% as a decimal is 0.05, so it's 1 plus R over N. N is 12. All that to the N times the time, in this case 6. So whenever you guys have a compounding like monthly, daily, any way that's not continuously, you use this first equation here. So 2,000 plugged in for the P, 0.05 for our 5% interest, plugged in for R. N was, since we compounded monthly, N was 12, and T was the 6 years that we had stuff out for. For continuously, it's A equals PE to the RT. So it's going to be A equals 2,000 E to the interest rate is a decimal, 0.05, times the 6 years that we run it out for. So let's use Desmos to figure out what our numbers are here. So 2,000 times 1 plus 0.05 divided by 12 all that to the power of 12 times 6. So we get 2698.04. We'll say we're round to the nearest cent. So 2698.04. So that's what happened when we compounded 12 times per year. Compounding continuously is you're compounding every single second that you possibly could. So this will be a little bit larger than compounding 12 times because we're compounding kind of all the time. So if we put that A equals PE to the RT in, so let's say we got 2,000 times E to the power of 0.05 times 6. This should be a little bit larger than the 2698, and we get 2699.72. So it's like $1 more because you're compounding more times per year. So actually, it's not even that much. 2699.72. And for these present value, future value types, you use those equations, and this is how the answers that are generated. This is how the answers that are generated look. Okay, so we're going to do two last one of these, then we'll say that that's good for the section. That should be all the different types they touch on in the homework. Let's see here. So last two here. Let's get this one out of the way, then we just got one more. So let's say we want to find the present value of $4,000 at an interest rate of 4%. Oops, sorry. Let's say at a rate of 6%, and we'll say compounded semi-annually. For 10 years. So since we're compounding not continuously, we're going to be using the first equation A equals P times 1 plus R over N to the NT. And they're basically asking us to find the present value. So they want us to figure out what this P value is this time. So they're telling us the present value of $4,000. $4,000 is the future value. That's what the present value has grown to. So we're going to use P as a placeholder for the present value. 6% is our interest, so 0.06 divided by semi-annually means twice per year. So we divide it by 2s, and then that's over 10 years. So I got P times this whole block of stuff here. So if you want to undo a multiplication, you divide. So we basically end up with 4,000 divided by 1 plus 0.06 over 2 to the 2 times 10 power. We just divide this whole mess across, and that will equal what our P is supposed to be. So this is 2 times 10 right there. So we're going to, again, go back to our Desmos, type this in, and see what it says that we end up with from doing that. So we get 4,000 divided by, 1 plus 0.06 divided by 2, all that to the power of 2 times 10 is 20. I guess we can write it just 2 times 10 if we want it. Oops. I guess we better just write it 20. And that gives us 2,214.7. So that was the initial amount I invested. Sorry, I dropped my pen here. So that's the initial amount I invested. So 2214.7. So if you invest this at 6% for 10 years, that will eventually grow. The 2214.7 eventually grows into $4,000 over the 10-year period. Okay, final one is going to ask us to solve out for the interest rate. So this last one, we want to find R. Find R for $3,000 to grow to $4,000. So we want to know $3,000 grows to $4,000 over 6 years. With interest, compounded quarterly. So, let's see here. What do we do? We're using A equals P times 1 plus R over N to the NT time again. A is the $4,000 we're growing to. P is the principal $3,000 we're starting from. We get 1 plus the interest rate's what we're curious about. Quarterly is N is 4. And we're saying grow over 6 years. So step 1, I need to divide the 3,000 across. So I get 4,000 divided by 3,000. So my goal is to solve this equation here for R. So I'm moving the 3,000 over by dividing it. That leaves 1 plus R over 4. 4 times 6 is 24, so that's to the 24th power. When we want to undo a 24th power, we take plus minus a 24th root. Since we're undoing even power with even root, we need a plus minus. Since this is money and the way things are working out, we're going to ignore the negative root. So we're going to get the 24th root of both sides. in order to cancel the 24th power. 24th root could be written as the power of 1 over 24. And 4,000 divided by 3,000 reduces to 4/3. So we're going to write the left-hand side as 4/3 to the 1 over 24th power equals 1 plus r over 4. So 4/3, 4,000 divided by 3,000, that's the ratio 4 over 3. And if you guys have a 24th root, you can write that as 1 over 24th as a power. So then I need to subtract 1 across. And then the final thing I need to do is I need to multiply this 4 to this whole mess. So we're going to put this in parentheses. We'll multiply this side by 4. And that 4 multiplies out there. And that'll leave our r by itself. So I need to figure out what is 4/3 to the 1 over 24th power minus 1, and then that entire thing multiplied by 4. So we want 4 times 4/3 to the power, the 4/3 is raised to the power of 1 over 24. And then we have a minus 1 after that. And we close out our parentheses. Let's see, so 4 is multiplying to everything. So this gives me 0.048. So 0.048 is r. If I move the decimal place 2 points over, that gets me the interest rate as a percentage. So a 4% interest rate, or 4.8% interest rate, will have the $3,000 grow to the $4,000 over the 6-year period. So that's basically it for section 4.2. If you guys got questions with it, shoot me an email and I can get back to you on it. But that should hit all the different bases of section 4.2.